Okay, thank you so much. I'm Nicole Lloyd-Ronning, and it's my pleasure to introduce Dr. Kate Alexander, who is a NASA Hubble Fellowship Program Einstein postdoctoral fellow at Sierra at Northwestern University. Her research focuses on transients of various types, but notably gamma ray bursts and tidal disruption events. And today she's going to talk to us about tidal disruption events, so I will hand it over to Kate. Thank you.
Thank you very much. I'm just going to start my screen sharing. All right. Everyone seeing my slide view?
Yep, looks good.
All right, great. Thank you very much, Nicole, and thank you to everyone for organizing this mini conference and attending. I'm really excited to come to the full conference next year, but I've also really been enjoying coming to this smaller conference right now. So I'm very excited to be here and hope to tell you all a bit about why I think tidal disruption events are so interesting. So I just wanted to start by setting a little bit of context for why we might want to study tidal disruption events. So as we know now through multiple lines of observational evidence, pretty much every galaxy of a certain mass hosts a supermassive black hole and at its center. And these supermassive black holes influence their galaxies in many important ways. So for a small fraction of supermassive black holes, they are actively accreting matter, and they may actively produce very large dramatic radio jets like we see here, which of course are interesting from a multi-messenger perspective because they may accelerate high energy particles. But most of the galaxies in the universe do not have such active supermassive black holes at their centers. Most galaxies, the supermassive black hole is fairly quiescent. And because it's fairly quiescent, it's not giving off a lot of electromagnetic light. And so therefore, as astronomers, we still find them somewhat hard to study unless we're incredibly nearby. This video that it looks like played through once is showing the orbits of stars around the supermassive black hole at the center of our Milky Way. But obviously it's impossible to resolve these stellar orbits for anything but the most nearby supermassive black holes. So what we would really love is a probe by which we can study the supermassive black holes in both the quiescent and the active phase in other galaxies at larger distances. And this is exactly where tidal disruption events, or TDEs, come in. So for the purpose of this talk, what I mean by a TDE is a star that gets scattered off of its normal orbit and such that it passes within the tidal radius of the supermassive black hole at the center of the galaxy. As the star approaches the supermassive black hole, eventually the tidal forces will overcome its self-gravity. The star will get torn apart, and some of the gas that was initially part of the star will end up accreting onto the supermassive black hole. So this is a very multi-messenger process. The actual accretion phase will create a luminous flare of light across the electromagnetic spectrum. You'll get thermal emission peaking in the ultraviolet or soft X-ray. Sometimes you'll get jet formation, so then you get high energy emission and radio emission. And recently there was a paper that reported that sometimes you also may see high energy neutrinos during this phase. So TDEs have gone from being a theoretically multi-messenger event to possibly definitively observed multi-messenger phenomena. And of course, the other possibility for TDEs is if you have a compact object in spiraling, you may actually generate gravitational waves, or you should generate gravitational waves from this process as well. We call this an extreme mass ratio in spiral event. And there are future gravitational wave facilities planned that may be sensitive to these kinds of mergers if they happen nearby. But since I am a radio astronomer and many of the people here are also radio astronomers, I'm going to focus mostly on what we can learn from radio observations of TDEs and how this may relate to multi-messenger observations that we'll be able to do in the future. So in particular, radio observations are interesting because they allow us to probe jets and outflows launched by TDEs during this period of temporarily enhanced accretion. And so a normal AGN jet, if it has a lifetime of thousands or even millions of years, it's very rare to see it turn on and off. But during a TDE, the black hole is temporarily accreting matter at a highly enhanced rate. So you actually get to see the full life cycle of a jet from its birth to turning on and then shutting back off again. So this allows us to try to answer some important open questions like, how do these jets actually form? What physical conditions do you need? How are particles accelerated? Again, neutrino observations may play a role here. How do TDEs fit into the broader picture of accretion onto supermassive black holes and their growth throughout cosmic time? Can we learn something more general about fundamental accretion processes by studying TDEs and their condensed timeline? And then also, what do the environments around black holes that were until recently not accreting at a high rate look like? As I said before, these are usually very fairly dormant systems, so they're harder to study at large distances, and TDEs provide us a window to do that. So how do we actually go about taking observations of outflows launched by TDEs? Well, the easiest way to do this is to study the synchrotron emission generated by the outflow. So if you have an outflow colliding with the ambient medium that was already there, it'll create a shock and enhance magnetic fields, and you'll get synchrotron radiation, which is a very well understood physical process. So you get a very simple broken power law spectrum. And if you can measure the overall normalization of the spectrum in these break frequencies, you can directly infer the physical properties of the synchrotron emitting material. So you can infer the energy of your jet or outflow, you can infer the density of the surrounding medium, you can learn something about the shock physics by which particles are accelerated in the shock. And by tracking this over time, you can build up how all of these parameters change with time. And we've actually been able to do this for some TDEs. This is a particularly beautiful example, the tidal disruption event Swift J1644, which was discovered in 2011, and we're actually still able to observe with radio telescopes today. So you can see in this multi-panel plot that the synchrotron SED is tracked all the way from 5 days to nearly 2,000 days after discovery, and the peak moves from high to low frequencies, and you can actually track things like how the energy contained in the radio emitting region changes over time. So in this case, we actually see the energy appear to increase for a while as the fastest moving material slows down, and slower moving material can start to participate in the shock acceleration process. And then it plateaus at a final energy value of a few times 10 to the 51 ergs, which is a fairly energetic relativistic jet. So radio observations of tidal disruption events have been a real growth industry in the past 5 years or so. In 2014, Swift 1644 that I just showed you was the only really well-studied tidal disruption event in the radio. We had a few upper limits suggesting that not all TDEs launched relativistic jets, but that was all we knew. And the situation as of this year, this is a figure from a review paper that was just published about a month ago, shows that now we have a whole menagerie of radio TDEs. And in particular, we now know that TDEs can produce both on-axis jets and off-axis jets, which makes sense. There's no reason that every TDE jet should be pointed right at us. And some of these TDEs that have even fainter radio emission may also produce non-relativistic outflows. So rather than a collimated jet, you may have something like a slower moving, less collimated wind. This is another mode of radio emission that we've seen in a few TDEs. And I want to particularly highlight on this plot AT 2019 DSG. This is the TDE I mentioned right at the beginning that may have a high energy neutrino associated with it. And what's interesting is that this TDE from its radio properties is luminous, but not particularly exceptional in any way. It's not one of these rare TDEs that launches a very energetic relativistic jet. So this is very exciting because it suggests that TDEs as a broader population may have the opportunity to contribute to the cosmic high energy neutrino population. So I don't have time to get into the details of some of the wonderful data that's available on individual events, but I did want to take a few minutes to talk about some of the things we can already learn from looking at these TDEs from a population's perspective. So this is just a plot showing the energy contained in the radio emitting outflows seen in TDEs versus how fast those outflows are moving. And so as a rough guide, TDEs and events that are on the right side of this plot are initially relativistic, and those on the left side of this plot were always observed to be moving at non-relativistic speeds, although still fast. This is a few percent the speed of light or so. And what's really interesting is that we already see evidence that the bulk of the TDE population produces these lower energetic, slower moving outflows, whereas a few percent of TDEs produce these much more luminous, much more energetic, highly relativistic jets. And for comparison, I've shown the stars in the background of this plot show the population of long gamma ray bursts with radio observations and the population of type 1b supernovae. Now, gamma ray bursts are known to occur during a subset of all observed type 1b supernovae. And so they are, but they do not occur in every 1b supernova. There's pretty deep limits on even an off-axis GRB jet in many of these nearby supernovae. So by looking at the population of GRBs and supernovae, we can infer that whatever conditions you need to produce an energetic collimated relativistic jet and have all of your energy from the central engine go there are fairly rare. And so what we are now beginning to see is that the same thing might be generically true in tidal disruption events, although it's a different physical scale. The physics governing relativistic jet formation may require some special conditions. And so one of the
4-minute warning. Sorry.
Thank you, Nicole. No, thank you. So one of the goals of building up a larger sample is to try to understand what makes the events that develop relativistic jets different from the bulk of the population. So, and then the other result I wanted to highlight from a population's perspective in this brief talk is looking at the other side of things. What can the TDEs and their outflows tell us about the environment around the supermassive black hole that was already there? So this shows as the outflow expands, it'll encounter density, and you can build up a density profile over time. And so this just plots the density profile for several TDE host galaxies, normalized to the Schwarzschild radius of their central black hole. Most of these are black holes of about 10 to the 6 solar masses. And then I've also included the density profile inferred around Sagittarius A star and around M87 for comparison. And one thing that's really interesting is that a couple of these TDEs have very steep density profiles around their supermassive black hole, which is not what you'd expect from something accreting at a fairly low rate with this with Bondi accretion, or something that's been modified by stellar winds like we see in Sagittarius A star, which has a much shallower density profile than some of these TDE host galaxies. So the fact that we're seeing these density profiles ranging between r to the -1 to r to the -2.5 in this sample of supermassive black holes is really interesting, particularly because at the typical distances of some of these TDEs, which can be 50 to 100 megaparsecs or more away, Swift 1644 was at a redshift of 0.3. There's no other way that we have right now to physically resolve these scales. So this is a very interesting observational glimpse into what's going on reasonably close to these black holes. So in my last minute or so, I just wanted to say, mention a couple of things I'm very excited about, ways we're moving forward to expand the sample of TDEs with radio observations. I also wanted to give credit to the optical wide field surveys, in particular ZTF, which have recently in the past year or so greatly expanded the discovery rate of TDEs. So we have more objects to follow up. We're developing new ideas for how to go about following them up. Because the synchrotron emission for TDEs often peaks in the millimeter band at early times. If you're looking to understand what's going on in the earliest phases of TDE outflows, ALMA is a wonderful facility for this. We've had a program on ALMA that I've been leading to do that. The first results for that are in prep and should be out soon. And in collaboration with some other folks, I just got a VLA large program approved to study all nearby tidal disruption events in the radio over the next 2 years. And I'm really very excited about this. I think this is going to make those population plots I just showed even more exciting. And we soon will have a much better sense of particularly what's going on in some of these radio quiet events where sometimes the source of the radio emission has been a little ambiguous. And in parallel, we have some blind radio surveys which may find TDEs in the radio. So sometimes it's hard to discover TDEs in the centers of dusty galaxies, for example. They may be missed by optical and X-ray surveys. So doing a blind survey in the radio should give us an independent estimate of the true rate of TDEs, which will be very interesting, again, for thinking about galaxy evolution and questions like that. So I'll go ahead and leave up my summary. Again, I'll let you read it, but I just wanted to note that if you're interested in what I've said in my talk and you'd like to learn more about what we've learned from radio observations of TDEs, I'd invite you to check out my review paper, which was just published in Springer's Space Science Reviews and is also available on the archive. So thank you very much, and looking forward to chatting more during the discussion session later.
Thank you so much, Kate. We have time maybe just for like a 30-second question. There's a really good question in the Q&A. Can you comment briefly on the black hole mass distribution of observed TDEs?
Yeah, so they actually, so they track the distribution you'd expect pretty well, but we don't see any TDEs occurring around black holes of greater than about 10 to the 8 solar masses. And this is exactly what we would expect for true TDEs, because above 10 to the 8 solar masses, the tidal disruption radius is inside the event horizon of the black hole. So for massive black holes greater than 10 to the 8 solar masses, you would expect them to swallow most normal stars whole. And the distribution of masses of the supermassive black holes we see for TDEs support this picture. There's a good paper by Short Van Velzen, I think from 2018, that talks about this in detail.
Excellent, thank you. And we look forward to talking more about this in the discussion section.